Hi everyone, this is your video on Extrema, and this video is going to be showing you how to find Extrema on a closed interval. Now that's going to be really important because we're learning 4 total different tests, and this first test is on a closed interval. The next test that we're going to do is on an open interval, meaning it goes like left to negative infinity and right to infinity forever. It's unbounded. We're going to be on a closed interval, which has like the brackets like this. So in order to go over a couple key vocab words here, can you pause the video for a moment here and sketch this graph for yourself, because we're going to mark it up a bit and talk about like where the vocab is and how it works. And before I start talking here, I just want to point out and make sure you got this here. Extrema. What do we mean by extrema? The most simple way of thinking of extrema is it's the largest or the smallest value. So again, what we're going to do in this video is figure out how calculus can help us find the largest and smallest values of a function on a closed interval. All right, so you should have sketched this graph here. Another thing you might want to do before I start talking is just jot down this kind of table, I guess, here for yourself so you have it as a reference. This table are the keywords we're going to be using whenever we solve these problems on our mission to finding absolute max and min on a closed interval. Okay, so you already have heard the words local min and local max. Local mins would be like A, C, E, G, and I. Now you might be thinking, isn't G the absolute min? You can call an absolute min a local min. It's kind of like how you can call a rectangle a square. So these are all local minimum. And then what we also have are local maximum. Local maximum, that will be like the largest value in that region. So what do we have here? B, D, F, and H. So those are high points on the graph. It looks like point D is the highest out of all of them, but I can still call it a local max because it's the highest point in its general region. All right, so other words, and this is what we really care about in this video, because the test we're doing now, the Extrema test, is for global, or I say absolute more, absolute min and absolute max. That is like the whole point of this video, to find the absolute min and the absolute max on a closed interval. So for us, our absolute global min is G, our absolute global max is at point D. And that's like the smallest and largest value anywhere on your closed interval. Critical value, I believe you've heard the word critical value before. When we say critical value, it's anywhere where the derivative is 0, or I don't know if I've emphasized this enough, it's where the derivative does not exist. So you already know that things that make, well, the thing that makes a derivative 0 is if your tangent line is horizontal. What would make a derivative not exist? You could have a vertical tangent line, you could have a sharp point or a cusp as well. Like we have kind of a cusp and maybe a cusp or sharp point there. That's a critical value. Another thing, we're going to talk a lot about endpoints. And I'm going to talk about endpoints in a minute, A and I. I'll talk about those on the next slide. Okay, and then extrema. Extrema is just the general word for all of these points here, A through I, where any kind of relative or absolute max or min occur. And just so you know, A through I, they're not really like a specific X or Y value. It's just like it's just a label to give that point. Okay, so just to make sure you are totally good, because we're going to say these words a lot on the next slides. In extrema, the largest or smallest value in their surrounding area, it could be local or absolute. And a critical value of a function is any number C in the domain such that f prime of C is 0 or f prime of C does not exist. Now in this video, there's going to be some like side comments like this. Make sure you're jotting down those comments for yourself, because again, you're learning 4 different tests over the next 2 weeks, and those comments are going to be really helpful to you to look back on to help differentiate between the 4 tests, because it is very easy to mix them up. All right, so let's talk about how are we going to do the Extrema test, because it's really easy to pick out the absolute max and min when you're looking at a graph because they're like right in front of you. But the whole point of the Extrema test, remember we are doing the Extrema test, is to find this all out without a graph. All you're going to have is an equation. So how could you possibly find an absolute max and an absolute min if you're not even looking at the graph and you just have an equation? So let's think about this here. We're going to link the equation to a graph. You want to think if a derivative is 0, you have to be at a flat point. And if you're at a flat point, then you're definitely a max or a min in your region. So think about this here. If you think about any kind of minimum, whether it's relative or absolute or any kind of maximum, the minimum and maximum values are at flat spots, like just by definition. And at a flat spot, that's where the derivative is 0. But also just keep in mind, like you could have a minimum or maximum that looks like this. And here the derivative doesn't exist. So we do need to consider where the derivative is 0 or does not exist. Those are really the only possible points where you could have a max or a min, any kind of max or min. And because we're on a closed interval, this is actually a critical thing to keep in mind. What if I had a graph? I'm just going to do a quick sketch. You don't necessarily need to draw this sketch down, but it's more just so you like conceptually know what's happening. Let's say I'm on this closed interval here, and watch carefully. Whoop. And here. So here is my closed interval A to B. And my question is, where is the absolute max and where is the absolute min? If all you do is look at where the derivative is 0 or does not exist, you would only be looking here, here, and here. And that means you would miss the actual absolute maximum of the function, which is at an endpoint. So if you're on a closed interval, only if you're on a closed interval, you need to investigate the endpoints, because the endpoints could be your absolute max and min. And if you look at this endpoint here, the derivative isn't 0, and the derivative also does not exist. Like the derivative does exist there. So again, consider your endpoints. You could have a max or a min there. All right, so here are your basic steps. Again, jot this down for yourself. One more time, emphasizing this. We're on a closed interval, and I guess I am not making a big enough deal out of this, or maybe I am. We are finding absolute extrema. That's important because the next test is for relative extrema. You'll learn that in a few days. So anyway, to find, man, I really should have fixed this before I filmed. Okay, to find the absolute extrema on a closed interval AB, find the critical numbers. So set your derivative equal to 0 or it does not exist. Evaluate F. And this is also critical because on the next test you learn, you're going to be evaluating F prime. And then on the test after that, you're going to be evaluating F double prime. So for the Extrema test, you are evaluating the original function F at your critical values and your endpoints. And then you're going to have some information here. So you're going to use a table. And on the AP exam, I'm going to show you exactly how it should look. And when you look at the scoring guidelines, it'll also look like that. I'll show you a table because the table is really your justification, because you get points for justifying your answer. And then you do actually want to state the absolute max or min in like a little sentence. Remember, absolute max and min are the Y values. Okay, so let's go. I'm going to do 2 examples with you. One of them is just going to be a straight up polynomial, and one of them is going to be, it'll have like a fractional exponent in it. So it'll be a little more interesting here. So let's take this quartic function here on our closed interval, -1 to 2. Remember, a quartic, I have an even degree, positive leading coefficient. Both ends are going up. I'm only interested in -1 to 2. All right, I got the first step done because it's very, very basic for this example. I need the critical numbers, so that means I need to get the derivative. So I took my derivative and I just basically factored it here. So I need to know, when does the derivative equal 0 and when does the derivative not exist? Well, finding when the derivative is 0, that's easy. You just set it equal to 0. But look, this is a cubic. My derivative is a cubic. Cubics are smooth. They're differentiable. There's no asymptotes or anything. So this thing always exists. The derivative always exists. You'll never find a spot where it's DNE. So generally you really only have to think about a derivative being dne if there's like a denominator with a variable in the denominator. So in this case, I don't have to worry about that. So x is 0 and x is 1. These are my critical values, okay? So usually I'll just label them critical numbers. And what I need to do is evaluate my original function at the critical numbers and then evaluate my original function at the endpoints. Again, make sure you are writing these comments down. I know some of you like to avoid writing these comments, but I didn't write them for fun. Believe me, I didn't love writing this out myself, but it's really important for future problems to like jog your memory on some key points here. Okay, now we are going to use labels whenever we plug in for our work. Labels, you don't want that stamp saying offensive notation. Okay, so I'm going to do f of 0, and then I'm going to do f of 1. So I'm plugging these into my original, so that means I'm going to have 3 times 0 to the 4th minus 4 times 0 cubed. Well, that's 0. And then my function value at 1 is 3 times 1 to the 4th minus 4 times 1 cubed, which is 3 minus 4, which is negative 1. Okay, so now let's do our endpoints here. And our endpoints were given. They're negative 1 and 2. Your endpoints are always going to be given. So I need to find f of negative 1 and f of 2. So I'm just going to plug those in real quick here. 3 times quantity negative 1 to the 4th minus 4 times quantity negative 1 cubed. So what is that? Oop, that's getting a little messy. 3 plus 4, which is 7, and that'd be 3 times 2 to the 4th minus 4 times 2 cubed, and that would be 3 times what, 16, so that's 48 minus 2 cubed is 8, 8 times 4 is 32. Okay. 16. Well, I think we have a winner here for the absolute maximum because that was the biggest y value that we found. And remember, these x values, 0, 1, negative 1, and 2, are the only places where you could potentially have a max or a min, because those are the only places where the derivative is 0 or where there's an endpoint. So you don't have to think about any other x values. So the table, the way that it is shown on the exam is the way that we're going to be doing it. EP for endpoint, you can definitely write endpoint out. I'm always going to abbreviate it. So we're going to do it in order. Like if you were doing a number line from left to right, you have your left endpoint, you had 2 critical numbers in the middle, you had your right endpoint, negative 1, 0, 1, and 2. So, okay, we had negative 1, critical number, our right endpoint was 2. And you don't need to draw that number line. So I'm going to get rid of that. And at each endpoint, I mean, you can make your table look a little bit more table-ish by giving it some rows and columns here. So f of negative 1 was 7. F of 0 was 0. And sometimes my tables will vary a little bit. Like, I don't always do this column and that column. You know, you'll figure it out. But for now, I'm going to make it a little more complete. You definitely always want the x values and the y values. So anyway, you're just going to look at your table. You did all the hard work. Now all you have to do is pick out the absolute max and the absolute min. So the absolute min is going to be the smallest y value. The absolute max is going to be the largest y value. So there's a couple ways that you can write your conclusion statement. I'll do one of the ways on the slide, and then I'll do the other way on the second example. What if the question said, what is the absolute min? The absolute min is negative 1. If they said, where is the absolute min? You would say 1. This is my least favorite way to take a point off whenever I'm grading FRQs in class and collecting them, because people just either read the question too quickly or they forget that the max and min is a y value. So anyway, the absolute max is 16. It occurs at 2. Okay? So you will, if this was a free response, you would not get credit without the statement and without the table. You need the table because that's like your justifying work. And then you can't just like drop the table on your paper and be like, okay, reader, figure out what my answer is. You have to make it very clear to your reader, whoever that may be on game day, what your answer is. Okay, let's do the next one. Extrema. Example number 2. Find the extrema of the function 2x minus 3x to the 2/3 on negative 1 comma 2. So here's my closed interval. Find the critical number. So I have to get my derivative and set my derivative equal to 0. Okay, so 2 minus, I'm going to bring the 2/3 down. 2/3 times 3 is 2x to the 2/3 minus 1 is negative 1/3. I'm going to rewrite this, and you'll see why in a minute. F prime equals. Okay, now I'm going to write one more comment here, and this is the most common mistake I always see. Well, the most common mistake I see when people do these problems. You always need to get one fraction to find where f prime equals 0 or d and e. Because in order to find if the derivative doesn't exist, you need to set the denominator equal to 0. What would make something not exist? If it has a denominator and if the denominator equals 0. So that means like you need one denominator for this derivative. Okay, so I'm going to do some real quick common denominator work, and you all can do this common denominator work. So I have 2x to the 1/3, or 2 cube root of x minus, oh my god, minus 2 over x to the 1/3. Okay, cool. So I'm kind of running out of room here. I guess I'll go over here. Whenever the derivative equals 0, the derivative equals 0 whenever the numerator equals 0. Okay, so let's set our numerator equal to 0. So then I have this. X to the 1/3 is 1. And that means x is 1. If you really want to show it every step, you're cubing each side. So x is 1. And then in order to find where the derivative doesn't exist, what I'm going to do, that would be setting the denominator equal to 0. So let's go ahead and do that. I got to scroll up. Hold on. Whoop. Okay. So my denominator was x to the 1/3 equals 0. Again, if you cube each side, you get x equals 0. So those are our critical numbers. We have critical numbers at 0 and at 1. So now I'm going to evaluate my original function at the critical numbers, and I'm going to evaluate my function at the endpoints. Okay? So let's go ahead and plug that in here. I'm going to do f of 0 and f of 1. Okay, so I'm going to plug this in real quick here. 0 to the 2/3. Well, that's going to be 0. So I have a point 0, 0. And then 2 times 1 minus 3 times 1 to the 2/3. 1 to any power is 1. So I have negative 1 and 0 as outputs. And now let's do f of negative 1 and f of 3. Okay, so f of negative 1. Let's plug negative 1 into the function. Negative 1 to the 2/3. All right, negative 2. Then negative 1 to the 2/3. What is negative 1 to the 2/3? Just to make sure you're thinking about this properly. That is the cube root of negative 1 squared, which is the cube root of 1, which is 1. Okay, so what I'm looking at here is negative 2 minus 3 times 1. Negative 2 minus 3 is negative 5. All right, and then I have f of 3. So that would be 2 times 3 minus 3 times 3 to the 2/3. Okay, 6 minus 3 times, how am I going to do this? That'd be the cube root of 3 squared. 6 minus 3 times the cube root of 9. All right, that's not going to work out well for me. If you did it on a calculator, you would get negative 0.240. And that's okay. Like, you're just going to have a decimal in your table. Not a big deal. So let's do left endpoint. And I had 2 critical numbers, right? 0 and 1. Okay, yeah. So this is another way that you can do your table if you want to save yourself a column. And why not save a column here? Okay, my left endpoint was negative 1. I know that at negative 1, my output was 5. My first critical number I hit was 0. That output was 0. My next critical number was 1. The output was negative 1. And then I have an endpoint at 3. And I mean, I rounded that. It's like, negative 0.240. So look at your table, people. What is the largest value? The largest value that I am looking at right now is 5. So if someone said, hey, what's the absolute max? You would say 5. If someone said, what's the absolute min? You would say -1. So another way of writing your conclusion statement is just a little bit different. Is start off by saying what the min is, not by saying where it's at. So the absolute min is -1 at x equals 1. The absolute max is 5 at x equals -1. Okay. And I'm going to write this one more time. These are y values for what the max and min are. Okay, cool. So you should be good to go now in class. We're going to practice a bunch to make sure you're good to go. Bye.